Welcome to Math Dog, Episode 4. This is mostly to help Geometry A students prepare for this week's quiz. That's your only assignment. I'm going to go through the quiz version A with you, and then your work for this week is to complete version B and send me back a picture of your completed work. In last episode, Math Dog was a bit uncooperative, and I realized she needed just a little bit more positive feedback. Now, it's important to give just the right amount of positive feedback, so she's earned herself another Le Champion Award. We'll put that with the rest of her awards. Yesterday, on March 29th, I sent Geometry A students an email, and these two quizzes were attached. I'm going to work quiz A as notes. You can watch the video and use this to help you do quiz B, which you are going to complete and turn in to me by Friday. If you can print it out, that's the best. If not, write your answers, being careful to label it correctly, 1A, 1B, 3A, 3B, etc. And send me your neat work. If you can print the page and work on the page, that would be best. This goes back to an earlier important topic from fall of this year, in which we studied conditional statements, which are if-then statements. The if portion is the hypothesis, which we're going to call P. The then portion is the conclusion, which we're going to call Q. So the hypothesis of this would be you are too sick to go to school. It's okay if we shorten it a bit. So something like you are sick. We'll just leave it at that. The then portion is you stay home. Now, I'm okay if you shorten these a bit, but you have to put enough so I know what you're talking about. For example, in number 2, apples grow on trees. They want a conditional. So they want the whole thing. If apple, then grows on trees. All right, that's a conditional statement, if then. The converse is when we turn it around. Q implies P. The notation is handy. So this would be if grows on trees, then apple. Well, sometimes the converse is true, but very often not. This one is not true. A counter example is when you find one example where that's not true. So we need something that grows on trees and it's not an apple. So how about cherries? Okay, what's that, Math Dog? No, dog bones doesn't qualify. Dog bones don't grow on trees. Must grow on tree, but not an apple. Good idea though. Let's see. All dogs are mammals. Conditional, if, then. We know that's coming along. That's a conditional statement. So if it's a dog, then it's a mammal. Converse, if it's a mammal, then It's a dog. Now an Euler diagram, that's how you pronounce that funny name, Euler. An Euler diagram, you would say, well, here's a picture of all the dogs in the world. Here's Math Dog. And all the dogs are mammals. So there's other animals that are mammals, not just dogs, of course. So there's a nice looking Euler diagram. We can use that to help us with deductions. Fidget is a mammal. Can we conclude that Fidget's a dog? No, perhaps Fidget is a whale. Perhaps Fidget is an elephant. Perhaps Fidget is some other type of mammal, but not a dog. So on this one, we would have to say no deduction. You would write that in there. But if they tell us that Fido is a dog, well, Fido's in here with the rest of the dogs. So we can deduce, we can make the deduction that Fido is a mammal. We can link these ideas together. If you liked a movie, then you thought it was a good movie. If you thought it was a good movie, then you enjoyed yourself. We can link these up, what I like to call cutting out the middleman. You find your link. Let's see, good movie, okay, and you cut that out. That links the two. So here, if you liked a movie, then you enjoyed yourself. And you would write that out. That would be the conditional statement that you end up with. So if, like, movie, don't tell your English teacher I wrote that as a sentence. Oh my gosh, if, like, movie. Ho, ho, ho. Then, enjoy self. Another conditional statement. If it's Valentine's Day, then it's February 14th. All right, so we find our hypothesis and we find our conclusion. Now for the converse, we've done this a couple times now. You just change the order around. If February 14th, then Valentine's Day. Again, I don't mind if you abbreviate a bit. Now, the inverse is when you negate them or say not. So we'll go back to the original order. Valentine's Day implies February 14th. We'll keep that order, but we'll put not in front. So if not Valentine's Day, then not February 14th. These are sometimes true and these are sometimes not true. Okay? Inverse has the word not in it. A biconditional, and this will turn into a true biconditional, is when the idea can go either direction. They're both true. The converse is true and the original conditional is true. They're both true. So here we would say, it is Valentine's Day. Now a special phrase, if and only if it is February 14th. That's our special phrase, if and only if. That means it can go both directions. You could have started with February 14th. You could have said, it is February 14th if and only if it is Valentine's Day. Now that's the logic that we were studying last fall. We also did quite a bit of review of algebra. So let's take a look at some of. All right, second page. Well, here we have some geometry diagrams that we want to know about. Let's start with this one here. This is, in fact, a linear pair. We're going to circle all the things that it is. Now, if it's a linear pair, we know it must be supplementary. That means the two of them add up to 180 degrees when you put them together. And it also must be adjacent. Adjacent means they're next to each other, but next to each other in a special way. They must share a vertex. So let's take a look at some other linear pairs. Anytime you have a line and then a ray shooting off of that, that's a linear pair. Those two angles are adjacent, they're next to each other, and they share a vertex, and they add up to 180. Linear pair, linear pair. Hey, here's linear pairs all over the page. Look at that. Those two angles are a linear pair. Now this one, these are adjacent, but they're not a linear pair. They don't add up to 180. To be a linear pair, they must be supplementary. These are not a linear pair, and they're not complementary. Complementary, let's skip on down to this one. D is complementary. That's when two angles add up to 90 degrees. Only two angles now, not three, not four. Two angles add up to 90. If two add up to 180, they are supplementary. Are they adjacent? Yes, they are. They touch each other and they share that vertex. Now this one's trying to mess with you. This one's trying to get you to think that they're adjacent. But no, they're not. They don't share a vertex. Here, angle 2 has its vertex there. Angle 1 has its vertex there. No, they're not adjacent. Okay. Hey, how about some algebra review fun? Here we want to write the equation of a line. We have kind of a tricky formula, this one right here, which is your point-slope formula. It doesn't hurt at all to know that name. Point-slope formula. Well, I've written it here in blue, but we know we need the slope to use the point-slope formula. We need that slope. How do you find the slope? Well, to find the slope, you subtract your y's on top and your x's on the bottom. The y's you could subtract in either order that you choose. You could say negative 13 minus 5, but what the heck, I'm going to go the other direction. I'm going to go 5 minus negative 13. Y's on top, I say. Y's on top. The x's go on the bottom. Now, if I'm going to start with 5, I have to start with 12. I can go either order, but I can't mix and match. If I'm going to start over here on the left, I've got to start them both on the left. 12 minus negative 15. Now, be careful with negatives. You know what subtracting a negative does. It turns it into addition. So 5 plus 13, 18 up top. 12 plus 15, 27 on top. If we can reduce that fraction, we sure do want to. You don't have to write this, but in your head, maybe you write it. You divide by 9 there and divide by 9 there. We end up with a slope of 2/3. And that's our slope. So we're going to plug that right in, substitute that right in for slope. I've left x and y, the plain old letters stay letters. x1 and y1, you choose either point. Which one do you want to use? I like smaller numbers better. I'm going to usually use the smaller numbers. So this one is x, the 12 is the x, so it goes in for x1. X minus 12. And the y1, I'm going to plug in the 5. Substitute in the 5. Looks pretty good, yeah? Now we've got an equation of that line. We'd like to turn that into slope-intercept form. We'd like to turn it into y equals mx plus b. So we distribute the 2/3. Let's see what that gives us. 2/3 times x is 2/3 x. Can we multiply this out? Let's see here. It's a positive times a negative. I know it's going to be negative. Maybe I need to go and multiply this together elsewhere. Okay, fine. If you need to, how do you multiply fractions? Well, you put that over a 1. 2 times 12 is 24. 3 times 1 is 3. But could we simplify that a bit? Oh boy, it's starting to look hard now. Let's see. Let's bring this down here. And we'll just multiply these together. Let's pick a spot that we're not using. 2/3 times 12 over 1. I've already got the negative sign. I didn't even put that in here. So I could do some canceling. I could divide by 3. I could divide by 3. Oh boy, that makes it easier. 2 times 4 is 8. If I didn't do my canceling, I could still get the answer. 2 times 12 is 24. 3 times 1 is 3. 24 divided by 3 still would give me 8. Hey, let's get the y by itself. We'll add 5 to both sides, putting like terms with like terms. Isolate the y all by itself. Combine your like terms, and what have you done? You've turned it into slope-intercept form. Yay, slope-intercept form. That's our good old y equals mx plus b, which makes it a heck of a lot easier to graph. Folks, last section, we have some order of operations fun. We're going to start inside that parentheses. You know we are. 2 minus 6 is negative 4. That's the first thing we do. We don't go 5 minus 3. That's the trap. It sure looks easy to start there. Well, that'll be easy, but you get it wrong if you do. Start in your parentheses. Now you square it. Notice the negative 4 is wrapped in parentheses, so we're squaring all of it, including the negative. A negative times a negative gives you a positive 16. We'll bring that down. Now we're going to multiply 3 times 16. How are you going to show that? Do you want to put a dot in between? That would work. Or you could wrap it in parentheses again. Bring down the rest of your work. All right, let's see. Multiplying before adding or subtracting. So 5 minus 3 times 16, that's a good one to know. That is 48. And we have our plus 1. Now at this point, you can do it two different ways. You can say 5 minus 48, that's negative 43, plus 1. Or another way you could do it is put all your positives together in one big pile. 5 plus 1, that's 6. Put all your negatives in another pile. And either way, lo and behold, what do you end up with? Well, negative 43 plus 1 is negative 42. And 6 minus 48 is negative 42. Two ways to finish that one off. Next, order of operations again. We can't combine those in the parentheses. They're not like terms. So next up, multiplication. We're going to distribute that negative 2. Oh boy, do we need to be careful. We'll keep our 3x minus 2x. Oh, everybody's going to do that right. But you know what's going to get missed? we're not going to distribute this negative. Not everybody, but we want to. Negative times a negative is a positive 8. Boy, does that positive get lost. Those two negatives, people neglect to distribute that negative to the second bit. There's going to be some people putting -8 here, but not you because you're a math dog fan. Bring down your work. Put your like terms together. 3x minus 2x is 1x. Do you want to put a 1 in front? You could, but let's not. 8 plus 5, 13. All right, that one is finished. Now fractions. Fractions aren't nearly as bad as they seemed when you were little tykes and you're learning it for the first time. To add or subtract fractions, you need common denominators. So we will figure out what will 3 and 6 and 4, the denominators, D, down, denominator. What does the thing on the bottom, what do they all fit into? Well, 3 goes into 6 evenly, but 4 doesn't. So let's see, 6 and 6 is 12. 3 goes into 12, 4 goes into 12. Eureka! We've found our common denominator. I'm going to write that down first before I do anything else. And then I'm going to figure out what goes up top. What did you multiply 3 by to get 12? 3 times 4 is 12. So 4 times 4, 16. 6 times 2 is 12. So 1 times 2 is 2. 4 times 3 is 12. So 3 times 3 is 9. Okay, now we're going to put this together. Let's see here. On the bottom, we're going to keep our common denominator of 12. On the top, we'll combine all of our numerators. 16 minus 2 is 14. 14 plus 9 is 23. There you go. You just added up some fractions that did not have common denominators. You got the common denominator, and then you were able to combine them. Well done, folks. Hey, let's take a look at the instructions again for this week. You're going to find the attachment and print out Quiz B. If you can't print it, you're going to write out your work super neatly telling me which problem you are on, 6A, 6B, etc. And you're going to send me a picture of that by Friday, April 3rd. Thanks, folks, and good work.